Welcome! Today, we'll explore an interesting problem titled Special Binary String. This problem challenges us to work with unique string manipulation techniques, diving into concepts like recursion and parsing. Let's dive in and break it down step by step. A special binary string is a specific type of binary string that meets three key criteria. First, it consists entirely of the binary digits 0 and 1. Second, it is balanced, meaning the number of zeros is equal to the number of ones. Third, for every prefix of the string, the count of ones is always greater than or equal to the count of zeros. Now, given a special binary string S, the goal is to recursively transform it according to a set of rules. These rules involve partitioning S into the smallest possible number of special binary substrings, sorting these substrings in descending lexicographical order, and then concatenating them back together. The expected output is the lexicographically largest special binary string that can be obtained after applying these operations. The input string is guaranteed to be a special binary string, with a length between 1 and 50, and the output will also be a binary string after following this transformation process. Let's look at the first example to understand this process better. The input string is S equals 110110000. We begin by splitting this string into the smallest possible special binary substrings, 1110. Next, we sort these substrings in descending lexicographical order. Here, 10 comes before 1100 when sorted in reverse order. Finally, we concatenate these substrings back together, resulting in the output string, 11100100. This demonstrates how partitioning and sorting transform the input string into the desired lexicographically largest special binary string. In the second example, the input string is S equals 101100. Similar to the first example, we start by splitting the string into the smallest possible special binary substrings. Here, the substrings are 10 and 1100. Sorting these substrings in descending lexicographical order gives us 1100 followed by 10. When we concatenate these sorted substrings, the resulting output string is 110010. This demonstrates how the recursive splitting and sorting process ensures that the output string is the largest lexicographically possible. The third example presents the input string S equals 111000. This string is already a valid special binary string and cannot be split further while maintaining the rules. Since no recursive operations are needed, the output remains the same as the input, 111000. This highlights that if the input string already meets all the conditions and is in descending lexicographical order, no modifications are necessary. When considering edge cases, it's important to note that single character strings are not valid special binary strings because they cannot be balanced. Strings that are already sorted, such as 111000 or 10, will remain unchanged since they meet the conditions and don't require any transformations. For strings with multiple nested special substrings, like 11011000, recursive splitting and sorting are essential to achieve the correct output. Additionally, strings with substrings already in descending order, like 111000, should be left as is. These examples and edge cases help to clarify the rules and behavior of the algorithm under different scenarios. To tackle the problem of generating the lexicographically largest special binary string, we first consider the brute force approach. The intuition here is straightforward, since the goal is to find a valid and largest special binary string. One way to solve this would be to generate all possible permutations of the input string. From there, we can filter out the invalid strings by checking two conditions. First, that the string is balanced, meaning it has equal counts of ones and zeros, and second, that it is recursively valid as a special binary string. Once we have the valid strings, we can sort them lexicographically and pick the largest one. However, this approach has significant drawbacks. Generating permutations involves factorial time complexity, and the additional step of checking validity for each permutation further increases the computational cost. This makes the brute force approach impractical for larger inputs, as the number of permutations grows exponentially. While simple to understand, this approach is not suitable for efficient problem solving in competitive programming scenarios. A more effective strategy is the divide and conquer approach, which leverages the recursive structure of special binary strings. The key insight here is that a special binary string can be broken into smaller special binary substrings. By sorting these substrings in descending order and concatenating them, we can achieve the lexicographically largest result. To implement this, we start by identifying balanced substrings within the input string. A balanced substring is one where the count of ones equals the count of zeros, and additionally, every prefix of the substring has at least as many ones as zeros. Once we identify these substrings, we process each recursively to break them down further if needed. After processing, we sort the substrings in descending order based on their lexicographical value and concatenate them. This approach directly builds the solution by exploiting the nested structure of special binary strings, significantly reducing unnecessary computations. While the recursion and sorting steps introduce a complexity of O(n)², this is far more manageable compared to the exponential growth in the brute force method. The divide and conquer approach offers several advantages. It is computationally efficient and operates well within the problem's constraints. By leveraging the recursive nature of special binary strings, the method avoids the pitfalls of generating and validating all permutations. However, it is important to note that this approach is slightly harder to implement compared to brute force. It requires careful handling of the recursion and sorting logic to ensure correctness. Despite this, the divide and conquer approach aligns naturally with the problem's structure, making it a clear choice for solving the problem efficiently. Instead of brute forcing through potential solutions, this method works directly with the properties of the binary strings, reducing redundant computations and focusing only on the substrings that are relevant. When comparing the two approaches, the divide and conquer method stands out as the superior choice. The brute force approach, while simple and intuitive, is computationally infeasible for larger inputs due to its factorial time complexity. On the other hand, the divide and conquer strategy strikes a balance between efficiency and clarity. It avoids the exponential growth in computation by directly working on the structure of the input string and recursively solving smaller subproblems. However, this approach does require careful implementation, particularly in identifying balanced substrings and ensuring the sorting logic is correct. The trade-off is that while the implementation may be more complex, the recursive strategy is a natural fit for this problem. Special binary strings inherently exhibit a nested structure, and the divide and conquer method takes full advantage of this property, making it both efficient and elegant for solving the problem. To begin, let's understand the nature of special binary strings. These strings are composed of only zeros and ones, and they follow two important rules. First, they must be balanced, meaning the number of ones matches the number of zeros. Second, they must be prefix balanced, which ensures that at no point in the string does the count of zeros exceed the count of ones. With these properties in mind, our objective is to transform a given special binary string into the lexicographically largest valid string. The input is a single binary string, which is guaranteed to meet the requirements of a special binary string. Now, let's break the algorithm into clear steps to achieve this transformation efficiently. The first step is to identify the smallest special substrings within the input string. A special substring is a segment that is both balanced and prefix balanced. To do this, we use a counter initialized to 0 and iterate through the string. For every 1 encountered, we increment the counter, and for every 0, we decrement it. When the counter returns to 0, we have found a valid special substring. Once identified, the next step is to process each substring recursively. For each substring, we remove the outermost 1 and 0, reducing something like 1100 to 10. The algorithm is then applied recursively to the inner portion, such as 10, to handle any nested structures. After processing the inner portions, we move on to sorting the substrings in descending lexicographical order. This sorting step is crucial because it ensures the final string will be the largest possible. After sorting, the algorithm proceeds to rebuild the string. Each sorted substring is wrapped with its outermost 1 and 0, restoring it to a valid special substring. These wrapped substrings are then concatenated together to form the final result. The completed string is the lexicographically largest special binary string derived from the input. There are two key insights that make this approach effective. Firstly, the recursive nature of the problem aligns with the structure of special binary strings, as they can be thought of as nested, similar to balanced parentheses. Secondly, the sorting mechanism ensures that the largest combination is chosen, making this step indispensable to the algorithm. An additional insight is the importance of the balanced prefix property. This property guarantees that substrings can be processed and recombined independently without breaking the conditions of a special binary string. The algorithm is designed to leverage this property, allowing efficient processing of the input. Speaking of efficiency, the method avoids brute force approaches, such as generating all possible permutations, by working directly with the inherent structure of the string. To implement this, we rely on a few key data structures. String manipulation is used to identify and process substrings. A simple counter is employed to track the balance during iteration, and substrings are stored in a list to facilitate sorting. Together, these components make the algorithm both systematic and efficient. Finally, let's analyze the complexity of this algorithm. Identifying special substrings within the string has a time complexity of O(n), where n is the length of the input string. Sorting the substrings adds a complexity of O(k*log k), where k is the number of substrings. The recursive processing depends on the depth of nesting within the string, which contributes to the overall complexity. In terms of space, additional memory is used for recursion and storing substrings. This space usage is proportional to the depth of recursion and the number of substrings. By carefully combining recursion with sorting and leveraging the structural properties of special binary strings, the algorithm achieves both time and space efficiency, making it well suited for handling large inputs. Here, we define the makeLargest special function inside the solution class. The first step is to handle the base case. If the input string s is empty, we simply return it as there's nothing to process. Next, we initialize three variables. Count is set to 0 and is used to track the balance between the number of ones and zeros in the string. Start is also set to 0 and will mark the beginning of a potential special substring. Finally, we create an empty list called special_substrings to store all the special substrings we identify. We then iterate through the string using a for loop. For each character, if it's a 1, we increment count. If it's a 0, we decrement count. These updates allow us to track when the string becomes balanced. Now, if count equals 0 at any point, it means we've found a valid special substring. At this point, we recursively call makeLargestSpecial on the inner portion of this substring, which is everything between the starting index plus 1 and the current index. The result is then wrapped with 1 and 0 on either side, and this newly formed substring is added to special_substrings. Finally, once all substrings are identified, we sort them in descending order. This sorting step is crucial because arranging the substrings in this way ensures that the final result is lexicographically as large as possible. After sorting the special substrings in descending order, the next step is to concatenate them into a single string. This is achieved using the join method on the special_substrings list. The resulting concatenated string represents the largest special binary string that can be formed from the given input. Finally, we return this string as the output of the function. With this, the implementation is complete, and the function effectively transforms the input string into the lexicographically largest possible special binary string by leveraging recursion, sorting, and careful substring manipulation. Here, we start by defining the makeLargestSpecial method, which takes a binary string s as input. If the string is empty, we simply return an empty string as the base case. Next, we initialize a count variable to track the balance between ones and zeros, and a start variable to mark the beginning of a potential special substring. We also create a list called special substrings to store all the special substrings we find. The logic for finding these substrings begins with a loop through each character of the string. For every 1, we increment the count, and for every 0, we decrement it. When the count becomes 0, it means we have encountered a valid special substring. At this point, we recursively process the inner portion of this substring, excluding the outermost 1 and 0, by calling the makeLargestSpecial function on it. We then construct the current substring by appending 1, the processed inner part, and 0 together, and add it to the special substrings list. Once we've identified all the special substrings, the next step is to sort them in descending order. This ensures that we maximize the lexicographical value of the resulting string. To do this, we use the collections.sort method with collections.reverseOrder passed as a comparator. After sorting, we concatenate the substrings in their new order. We use a string builder to efficiently append each substring from the special substrings list. Finally, we return the resulting string, which is the largest lexicographical special string that can be formed from the input. This approach leverages recursion and sorting to break down the problem into smaller parts and ensure the final result is optimal. We begin with the input string s equals 110110000. To start, we initialize three key variables. Count is set to 0, which will help us track the balance of ones and zeros. Start is set to 0, marking the beginning of our current substring, and an empty list special underscore substrings is prepared to store valid special binary strings. As we iterate through the string, we process each character one by one. At index 0, the character is 1, so we increment count to 1. At index 1, we encounter another 1, and count increases to 2. At index 2, the character switches to 0, so we decrement count back to 1. Then, at index 3, another 0 brings count back to 0. This indicates that we've found a special binary substring. We extract the inner part of the substring from s, start plus 1i, which gives us 10. Since 10 is already a valid special binary string, we return it as is. We then construct the full substring as 1 plus 10 plus 0, which equals 1100, and append it to special underscore substrings. Finally, we update start to 4 to begin looking for the next special substring. Now, the iteration continues from where we left off. At index 4, the character is 1, so we increment count to 1. At index 5, another 1 increases count to 2. At index 6, the character is 0, so count decreases to 1. At index 7, another 0 brings count back to 0, signaling that we've found another special binary substring. We extract the inner part from s, start plus 1i, which is again 10. Recursively processing 10 returns 10, and we reconstruct the full substring as 1 plus 10 plus 0, resulting in 1100. This is added to special underscore substrings, which now contains 1100. Next, we sort special underscore substrings in descending order, but since the substrings are identical, the list remains unchanged. Finally, we concatenate the sorted substrings to form the output, which is 1100 plus 1100 equals 110110000. Thus, the output for this example is 110110000. In the second example, we take the input s equals 101100. Again, we initialize count equals 0, start equals 0, and an empty list special underscore substrings. As we process the string, at index 0, the character 1 increments count to 1. At index 1, the character 0 decrements count to 0. This tells us we've found a special binary substring. Extracting the inner part from s, start plus 1i, results in an empty string. Recursively processing this empty string gives us. We then reconstruct the substring as 1 plus 0, which equals 10. This substring is added to special underscore substrings, and we update start to 2 to continue processing the remainder of the string. We proceed by iterating through the rest of the string. At index 2, the character 1 increments count to 1, and at index 3, another 1 increases count to 2. At index 4, the character 0 decrements count to 1, and at index 5, another 0 brings count back to 0. This marks another special binary substring. Extracting the inner part from s, start plus 1i, gives 10. Recursively processing 10 returns 10. We reconstruct the full substring as 1 plus 10 plus 0, resulting in 1100, which is added to special underscore substrings. Now, special underscore substrings contains 10, 1100. Sorting these in descending order gives special underscore substrings equals 1100, 10. Joining the sorted substrings results in 1100 plus 10 equals 110010. Thus, the output for this example is 110010. Finally, in the third example, we take the input s equals 10. We initialize count equals 0, start equals 0, and an empty list special underscore substrings. As we iterate, at index 0, the character is 1, so we increment count to 1. At index 1, the character is 0, so we decrement count to 0. This indicates a special binary substring. Extracting the inner part from s, start plus 1i, results in an empty string. Recursively processing this empty string gives. We then reconstruct the substring as 1 ++ 0, which equals 10. Adding this to special underscore substrings results in special underscore substrings equals 10. Sorting is unnecessary since there is only one substring. Joining the substrings gives the output 10. Therefore, the result for this example is 10. To analyze the time complexity of the make largest special function, we begin by examining the recursive parsing process. The function operates recursively, breaking the input string into smaller special binary substrings. For an input string of length n, this parsing requires a single iteration through the string at each level, resulting in a time complexity of O(n) per recursive level. Next, after parsing, the function sorts the special substrings. If there are k substrings, sorting them costs O(k*log k). In the worst case, the number of substrings at any level can reach up to n/2, such as when the string alternates between 1 and 0. This means the sorting step at each level has a cost of O(n/2, *log n/2. Finally, the recursion depth itself is determined by the nesting of special binary substrings. In the worst-case scenario, where each recursive call reduces the string by one outer 1 and 0, the recursion depth can be as high as n/2 levels. Now, combining these factors, the total time complexity at a single recursion level is the sum of the parsing cost, O(n), and the sorting cost, O(k*log k). Across all recursion levels, the dominant factor influencing the total cost is sorting. This leads to a worst-case time complexity of O(n²*log n), where the quadratic term n(2) arises from the cumulative processing across all recursion levels, and the log n comes from the sorting operation. Shifting to space complexity, the key contributors are the recursive call stack and the storage needed for substrings. The recursion depth, as mentioned, can reach O(n/2) in the worst case. Since each recursive call has a constant memory overhead, the stack memory usage can be approximated as O(n). Additionally, at each level, the function stores a list of substrings, with a maximum of n/2 substrings at the top level. Each substring can take up memory proportional to the input size n, meaning the memory for these substrings is also O(n). Overall, the space complexity of the function is determined to be O(n). Comparing this optimized approach to a naive brute force method highlights significant improvements. A naive solution might involve generating all possible permutations of the binary string and checking each one for validity as a special binary string. This process would result in factorial complexity, O(n), which is computationally infeasible for larger inputs. In contrast, the optimized approach avoids unnecessary permutations by recursively leveraging the properties of special binary strings and sorting them to construct the largest valid result. This reduces the time complexity to O(n²*log n, providing a dramatic improvement over the naive approach. When considering best, average, and worst cases, the best-case scenario occurs with flat strings that lack nested special substrings. Here, the recursion depth is minimal, and sorting costs are lower, leading to a reduced time complexity of O(n*log n). However, in highly nested strings, the recursion depth increases, and sorting at each level becomes the dominant factor, giving the worst-case time complexity of O(n²*log n). When solving problems involving special binary strings, it's crucial to avoid some common mistakes. First, failing to validate the properties of a special binary string can lead to incorrect solutions. Remember, a special binary string must have equal numbers of ones and zeros, and for every prefix, the count of ones must be at least as high as the count of zeros. Neglecting this validation can result in invalid strings or logic errors. Another mistake is ignoring the recursive structure of the problem. Special binary strings can be broken down into smaller valid components, which are sorted and combined recursively. Approaching this iteratively or without leveraging recursion often leads to incomplete or inefficient methods. Finally, sorting the substrings incorrectly is a common pitfall. Sorting them lexicographically might seem intuitive but does not satisfy the problem's requirement to arrange them in descending order based on their value. Sorting must align with the recursive structure to ensure correctness. Mismanaging substring splits is another frequent challenge. When dividing the binary string into valid substrings, precise tracking of indices is essential. Losing track of indices can result in invalid substrings or skipped characters, which compromises the solution. Additionally, overcomplicating the base cases is a mistake to avoid. The base case is simple: if the string is empty or already a valid special binary string, no further processing is needed. Introducing unnecessary checks or additional conditions at this stage can make the implementation harder to follow and more prone to errors. Keeping the base case straightforward ensures clarity and reduces potential mistakes. Special binary string problems are often used in interviews to test a candidate's grasp of recursion, divide and conquer, and greedy algorithms. Interviewers tend to focus on how well candidates recognize patterns, such as the recursive nature of the problem, and how they optimize their solutions. A clean, modular approach is highly valued, with functions dedicated to validation, sorting, and combining substrings. This not only demonstrates clarity but also improves maintainability. Time complexity is another critical discussion point. The optimal solution typically involves O(n), time for splitting the string into substrings, and O(k*log, k, for sorting, where k is the number of substrings. Understanding these complexities and being able to explain them is key during interviews. Several related problems on LeetCode can help build the necessary skills to tackle special binary strings. For instance, problem 22, generate parentheses, also involves generating and validating strings based on balanced properties, akin to the balance of ones and zeros here. Problem 301, remove invalid parentheses, requires balancing characters and leveraging recursion, making it a useful practice problem. Problem 1249, minimum remove to make valid parentheses, focuses on preserving valid structures in strings, while problem 241, different ways to add parentheses, shares the divide and conquer and recursion techniques necessary for this challenge. As for alternative approaches to solving special binary strings, a brute force method involves generating all permutations of the string and validating each one. However, this is computationally expensive, with a time complexity of O(n). Not feasible for larger inputs. On the other hand, a recursive divide and conquer approach, which involves splitting, sorting, and recursively processing substrings, is optimal but requires careful handling to ensure correctness. An alternative to recursion is iterative parsing with a stack, which can be used to track the balance of ones and zeros and identify valid substrings. This approach avoids the overhead associated with recursive calls, which might be advantageous in certain cases. However, it can be less intuitive than recursion, especially when managing the stack and ensuring correctness during substring identification. Each method has its trade-offs, and the choice often depends on your familiarity with recursion versus iterative techniques and the specific constraints of the problem. Great work! We've successfully broken down the special binary string problem. Remember the key strategies of recursion and sorting to simplify complex problems. Keep practicing and exploring similar challenges. Thanks for watching, and I'll see you in the next session. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!